Please welcome Kalman Lajko, engineer at zkSync. If you walk around, please use this.
Hey everybody, I'm Kalman Lajko from zkSync, previously at Slush, and I'll talk to you about hyperchains and hyperbridges. So how many of you here were for the StarCreate talk, which was a talk that was before the last one? So 2 of you, so not so many. Okay, this means that some of the concepts will be very similar, but then I will go over them again. I hope it will be better this time. So first we'll cover the road to hyperbridges, how we got here from the original Bitcoin and different scaling experiments. Then I'll cover a few different ecosystem architectures. So proof aggregation, layer freeze, also known as fractal scaling, then layered aggregation, which is a combination of layer freeze and proof aggregation, and has the benefits of both. Then there are 2 more things, fast messaging, which can be added as an add-on to layered aggregation, and finally I'll talk about atomic hyperbridges. After this I'll talk about hyperchain UX, so what it will feel like to use hyperchain, and finally I'll talk about the zk stack, which anyone will be able to use to launch their own hyperchain. Okay, so first, the road to hyperchain. So we all know this comment from the original Bitcoin white paper. We very, very much need such a system, but the way I understand your proposal, it does not scale to the required size. So the problem of scaling has been with us from the very beginning of blockchain. Bitcoin does around 7 transactions per second, Ethereum does 12, Visa does 2,000, and if we want to make crypto accessible for everyone on the world, it will have to be 100,000 TPS or maybe even millions of TPS. So it is quite a big challenge. And to achieve this, the end goal has been horizontal scalability. So horizontal scalability means that you should be able to spin up new chains and to handle the new traffic, just as you can spin up new servers to handle the traffic to your web page if you have more traffic. And these new chains have to be integrated trustlessly into the ecosystem, and this will happen using some sort of bridges. So Cosmos and Polkadot have both been examples that have attempted horizontal scalability, but for both of these attempts, the bridges are fundamentally not trustless, and this is because it's very hard to build good bridges. Vitalik posted about this. There are fundamental limits to the security of bridges that hops across multiple zones of sovereignties. So why is this? This is because it's very hard to generalize across bridges, but the usual problems are that usually they are not trustless. There are atomic swaps that are trustless, but those cannot be used for general message passing. General message passing bridges use some sort of economic mechanism. The bridges have some sort of governance mechanism that is independent from the chains. This is important because if the bridges are hacked, then the governance mechanism can interfere to fix the bug. But this is also an additional risk assumption. And finally, perhaps the biggest problem is that the chains can hard fork. And this is a very big problem because if you hard fork, then your previously sent messages need to be reverted on the destination chain. So this is very hard to solve the hard forking problem. So to solve the trustless bridging problem, there have been multiple attempts. The Lightning Network on Bitcoin, but also mainly on Ethereum, there have been much more attempts. So state channels, Plasma, sidechains, and optimistic rollups have all been attempted. It is clear now that zk rollups offer the most security due to the cryptographic nature of the security. zk rollups prove their execution, so they are the most secure. So using zk rollups, we can have trustless bridges. The bridges are trustless as execution is verified using cryptography. there cannot be hard forks as the bridges are enshrined. So what the layer 1 says about the state of the chain, that's the state of the chain. Similarly, the bridges are governed alongside the chains on a smart contract in L1 usually. So if the bridge is hacked, then the governance can interfere. And finally, assets can be burned and reminted natively between the hyperchains. So this is what hyperbridges are. Hyperbridges connect the different hyperchains. So how do hyperbridges work? And this is where it gets to start a bit more technical. When you're hyperbridging, there's a sending chain, in this case zkSync era. There's a destination chain, hyperchain, and there's the layer 1 shared bridge. So you initiate the transaction on the sending chain, you burn the asset that you're sending, you settle down a proof to the shared bridge. This shared bridge hosts a root of all messages. This root of messages commits to all of the transactions that are happening across all of the hyperchains. So this is not an expensive operation for a single transaction. After this, the destination rollup can import this message route. A relayer can relay the transaction to the destination chain. They also have to relay a Merkle proof connecting the transaction to the imported message route, and the transaction can be verified. If the transaction is verified, it can be executed, and the relayer is also rewarded economically. After this, the destination hyperchain has to settle its proof down to L1, and when this settles, it also settles the imported message route, and it has to be made sure that that's the same correct message route. So that is hyperbridging, and this works between all hyperchains in the ecosystem. It is trustless, as it is verified by the L1 ultimately in cryptography. It is also cheap, as transactions don't have to go through L1, and this is how we get ultimately horizontal scalability, because anyone will be able to launch their own hyperchain and be part of this ecosystem. So that's the basic architecture. Now let's dig a bit more into the details, like layer 3s, shared provers, etc. So what does the actual ecosystem architecture look like? So Vitalik wrote a great post about this. The title is, "What kind of layer 3s make sense?" He concludes it by asking the question, what even is a layer? So even this is a bit blurry area in this topic. And I quote, "There's clearly an important role to be played by layers of some kind. And there's clearly an important function of proof aggregation that needs to be filled somehow. I suspect that more sophisticated and simpler constructions, such as those described in this post, will start to have a bigger role to play as the layer 2 scaling ecosystem matures." So we'll go over these layers, also known as fractal scaling. This is good for fast messaging. We'll also go over aggregation. This is good for scalability. And we'll look at some more complicated, but perhaps even simpler constructions additionally. But before we start, for any construction, the hyperchains have to be sovereign. So this means that if you, for example, have a layer 3, the layer 3 will be able to quit the layer 2. And become its own independent and sovereign layer 2. And it will be able to settle to the shared bridge alone. Okay, so the first method is proof aggregation. So for proof aggregation, you have different hyperchains, and they aggregate their proofs together into a single proof and settle it together onto L1. This is great as it is scalable. Any number of hyperchains can aggregate their proofs, and the proof aggregator treats these statements as completely independent. Ultimately, the problem with this solution is that it does not allow fast messaging. In order to save costs, proof verification on the L1 will happen maybe every 30 minutes or 1 hour, depending on the actual rollup ecosystem. And until this time, messaging is not possible because for security reasons, you can only import a message after it has been settled onto layer 1. Otherwise, the sending rollup might revert, and you will have to revert as well because the transaction that you imported is now invalid. And this is where layer freeze come in. So layer freeze and layers in general allow fast messaging. If you're a layer freeze, you can settle onto a layer 2. You can do the same hyper-bridging process as before, just lift it up a layer. This is the same lines and same cycle. And because it's a layer 2, it's much cheaper than the layer 1. So this can happen much more often. And this is also a form of proof aggregation, because if we look at it in more detail, then what actually happens is that this message and proof message route importing and receiving the transaction will happen on different blocks of the layer 2 and layer 3. So that's block N of the layer 1 and of the layer 2 and layer 3, and this is the next block in each of the chains. And you can't import the message and the transaction before it's settled. And the layer 2's proofs for each block or each batch are aggregated together into a single proof, and this is settled together onto L1. So this is great, but the problem with this solution is that it does not scale, because the layer 2's virtual machine is fundamentally a bottleneck to execution, just as the layers 1 virtual machine is a bottleneck. What's more, the layer 2 is a full rollup. So this means that it needs a consensus mechanism, it needs a mempool, it needs long-term storage, it needs data availability, and this means that its validators will be completely independent from the layer 3 and the layer 1 validators. And currently, when there are mostly no decentralized rollups on Ethereum, there's only a decentralized L1. We don't see this problem yet, but in the future there'll be a large fragmentation of validators across the different rollups. So can we make this solution simpler, more scalable, but also keep the fast messaging that layers allow us to do? And this is possible. We just need to remove the virtual machine layer 2. We need to replace it with a specialized proof. The specialized proof will do the same things as a virtual machine did, but only for layer 3s. So it will only handle the settlement of the layer 3s and the messaging. It will not do additional transactions, and it will not be a full Turing-complete virtual machine. But because, and it will still need its consensus mechanism, so that hyperchains can make sure that it will not revert, and they can be secure in the settlement of other hyperchains. So this is good because it's a more scalable solution compared to the layer 3s. And because it is not a full virtual machine, the consensus mechanism does not need long-term storage. It does not need a mempool. It only needs to handle transient data that the hyperchains are always settling onto it. So if we compare the previous 3 solutions, we have simple proof aggregation. This does not allow fast messaging. It does scale, and it does not need a consensus mechanism. Layer 3s do allow fast messaging, but they do not scale. And the layer 2 needs a full consensus mechanism, which leads to validator fragmentation. Layered aggregation does allow fast messaging, It does scale due to the proofs and proof aggregation, and it only needs a lightweight consensus mechanism, which means that there will be less or no validator fragmentation across this consensus mechanism and the hyperchain layer freeze consensus mechanisms. Okay, so that was the 3 big architectures. There are also some interesting add-ons, such as instantaneous messaging. Here I have to disagree with the Starkware talk. Unfortunately, most of you weren't here, so I'm not going to compare solutions a lot. But instantaneous messaging is only possible trustlessly once the sending rollup has settled onto either a layer 1 or a layer 2. You can import the message route earlier, but then it might be incorrect. If it's incorrect, then you will have to revert your state and your rollup. So there can be some sort of economic guarantee that makes sure that the message route is correct, but this does not scale to a very big ecosystem, because if a single message route is incorrect, then the whole ecosystem has to revert, which is a very big problem. So the message route can be calculated before the proof is generated, separately from the proof, and it can be imported to settle transactions as before. And if there's an economic mechanism that makes sure that this message route is correct, then instantaneous messaging is possible. Another add-on, which is atomicity. I also think this is possible between hyperchains, but it is a very complicated construction, so I will not even go into full details here. Simplified version of the solution is that we not only record the sent message routes, but we also record the received message routes that all the hyperchains receive. And if the blocks for each hyperchain are generated at the same frequency, then the sent message routes and the received message routes can be compared. And they have to be the same. And if they are the same, then that means that all sent transactions are also received. So the hyperbridge is atomic. This also uses an additional feature, which is that in order to make sure that the receiving hyperchain can import the transaction, it has to be settled onto the DA layer. And it cannot be external relayers that relay this transaction. All hyperchains will need to scan the DA layer and scan the transaction that they received and import them. Now, hyperchains will not generate their blocks at the same frequency, so the actual construction is even more complicated and uses 2D KZG commitments to store the unconsumed transactions, but let's continue for now. So to conclude with the ecosystem architecture, there'll be the layer 1. This will host the shared bridge. The layered aggregator will settle onto it not very frequently. The hyperbridges will settle onto the layered aggregator frequently, and when they settle into it, other hyperchains will be able to consume the transactions that are sent to them. And we can also have trust zones, which are guaranteed by economic incentive mechanisms that allow instantaneous messaging. But for normally for the whole ecosystem, the messaging time will be the proof generation time, and the settlement time, proof generation time will be probably around a couple of seconds to a minute with zkSync's new proof system, and the settlement time is always chosen by the hyperchain. Okay, so let's talk about user experience. What will it feel like to use a hyperchain? So Vitalik also wrote about this in a deeper dive on cross L2 reading for wallets and other use cases. So cross L2 reading is the Merkle proofs used for hyperchains. He mentions cross-chain wallets, which are wallets that support multiple chains at the same time. These will be integrated into the native account abstraction on zkSync. He also talks about cross-chain proof aggregation. This is a performance improvement used to make hyperbridging cheaper. And he mentions privacy, which is also a long-term goal. So you will be able to send a transaction on a hyperchain. This will be relayed to another chain, for example, the Uniswap chain, where it will be executed. The swap will happen. 1 Ethereum will be converted, for example, 10,000 DAI. And this 10,000 DAI will be sent back to the original hyperchain. And you will only have to initiate the first transaction. The cross-chain hyperbridges will be settled by relayers in a matter of minutes, depending on the proof generation and settlement time of the specific rollup. You'll also have chain and identifiers such as era.zkSync, so it will be quite simple to send money to specific addresses on specific chains. So for smart contract devs, hyperbridges will be similar to L1 and the L2 bridge. They will be asynchronous. Specifically, they will be similar to the L2 to L1 bridge direction. Here, settlement time is the hyperbridging only happens once the proofs are settled, and it will not be atomic. There will be inbuilt nullifiers for function calls, so devs will not have to worry about double spends and double calls. We will start with economic guarantees for relayers, but we are also researching atomicity. And not just users and devs will not only be able to do transactions, but cross-chain views, such as viewing events happening on other chains or storage slots on other chains, etc. So finally, I'd like to say a few words about the zk stack. The zk stack is what will allow developers to launch their own hyperchains. The zk stack will consist of the current main zkSync era repos. So the core virtual machine and the prover will have to be the same across all hyperchains. This is what allows interoperability in the ecosystem. But other options such as data availability and sequencing can be freely chosen. So for example, for data availability, there will be the rollup mode, which is the most secure, where all state diffs are settled onto L1. There's also Validium, where the validators of the hyperchain handle the data. And there's also zk Porter, which is a fusion of the two, combining the good properties of both systems. Sequencing can also be chosen. It can be decentralized, which is of course the recommended one because this provides the most censorship resistance. It can be centralized. This will be good for some enterprise users. And finally, it can be based, so L1 sequencing. In this case, all transactions happening on the rollup will have to go through the L1 DA layer. And this is also a data availability solution. So if you're a base rollup, you will not have to post state diffs to L1. And other options such as privacy, MEV, shared sequencers, or external DA solutions can all be used. Only the core virtual machine and the prover are mandatory because that is what allows interoperability in the hyper bridges. So this is the zk Porter. The zk Porter consists of two shards: the rollup shard, which posts all state diffs to L1, and there's also a zk Porter shard. In the zk Porter shard, state diffs are sent to the either to an external DA layer or to the validators of the zk porter. And this is a great solution as for users who need security can use the rollup shard, and users that need cheap transactions can use the porter shard. And transactions between the two shards are atomic and synchronous, as they will happen inside a single virtual machine. So you will be able to use your porter account to make an atomic and synchronous transaction with, for example, a DEX on the rollup shard. Finally, I'd like to end with the zk Credo, which we think the zk stack needs to satisfy in order to be truly usable by the whole Ethereum community and ecosystem. It needs to be trustless and secure. This is guaranteed by zero-knowledge proofs. It needs to be reliable. This is guaranteed by audits and bug fixes and just time battle testing the system. It needs to be censorship resistant. This is guaranteed by L1 priority queue. You can force transactions through the L1, and the sequencer will also be decentralized. Private, this is harder to achieve. We're also, in the long term, privacy needs to be achieved for users. The system needs to be hyper scalable. This talk is about hyperchain, so I hope you know what that means. It needs to be accessible for a large number of users, and the rollups and hyperchains will also need to be sovereign. So thank you very much. If you want to go to more zkSync events, please scan this QR code, and I'd love to answer your questions.
Thank you, Kalman. Do we have any questions in the back? Hello, sir.
When is airdrop?
I'm not authorized to, I don't know. I don't even know if there will be an airdrop.
Great presentation. Just a question on the user and developer experience, in particular where you have the base chain, and then you have, I forget the exact term you used, but it was in green, and then you had the hyperchains plugging in and settling. I'm curious if, as a developer, how much of that stack do I need to deploy to or be familiar with, and likewise as a user, am I going to have to even know, for the mass use case that this is rolling up to Ethereum, or do you imagine applications directly doing fiat on-ramp to hyperchains? Maybe just talk a little bit more about the onboarding process for both those communities.
So for users and developers, or hyperchain developers?
Well, I'm assuming, so users from the point of, as a developer, I want to build hyperscalable apps, so I need to use a hyperchain. What is that process to deploy to the hyperchain? And likewise, as a user, or if I'm an app developer for users, am I doing fiat on and off ramp directly to that hyperchain? How do I communicate to users that they're on a hyperchain and not Ethereum? Curious what this rollout looks like with all the different interconnecting layers.
Okay, so I think initially you will write your application and run it on a public chain. And as you make it bigger and bigger, there will be probably hyperchain as a service providers, which you will be able to use that will manage your hyperchain for you. But if you want to, you will also be able to run your own hyperchain. And the requirements for this are running the sequencer, running the prover. There will be, the packages that are used by ERA will be provided, so you can decentralize both of these quite easily. But as you scale your app, you'll go through probably different phases. So you'll probably start on a public chain. You'll probably start out with a centralized hyperchain, and then you can decentralize it as it grows and you need more and more users. Did I answer your question? Or not?
Thank you for the talk. I wondered, does a hyperchain will need the zkSync era layer? because I have in mind the StarkNet architecture where there is StarkNet and then there are applications that are built on StarkNet. And here, from what I understand, you said that hybrid chains will be independent from zkSync area. So could you call them other layer 2s? Just a clarification on that, please.
So there'll be a lot of options. You will be able to launch your own layer 2. If you want, you will be able to launch your layer 3. You will be able to launch and use the shared provers. You will be able to use layered aggregator, which functions as a layer 2 as it will need its own consensus mechanism. So there'll be a lot of options, and each chain will choose the requirements that it needs.
All right, thank you, Kalman.